Welcome to the part C of lecture series 8. In this lecture, we are going to talk about Granger causal inference. In this lecture, first we will try to understand that correlation does not imply causation. This is a very important statement, and question is always why causation is important with respect to predictive analytics. So suppose we are modeling y equal to some function of x1 and x2. So x1 and x2 are two features. x1 and x2 are features. And you want to predict the value of y. If we know x1 or x2 has a causal effect of y, then we will be confident about the predictive power of the model. However, if the x1 and x2 does not have a causal effect on y, and what we observe a spurious correlation, then the model will fail in live production environment. So, and that is the time what happens is model don't generalizes. So you may heard, if you are coming from machine learning background or engineering background, that model don't generalizes in the live production environment. Why it's so? Because if you find a predictor which may be correlated for some spurious reason, and remember that what is correlation? Correlation is just a formula. End of the day, correlation is just a formula which, for whatever reason, is showing may show a high correlation between two variables. But if you know there is a physical phenomena, there is a domain relation, the domain do explain the relationship between a feature and the response, then you know whether it's a linear, non-linear, whatever be the relationship, you from the feature you can explain or you can expect y to behave in certain way, maybe with some uncertainty, but you know there is a relationship. In that case, your reliance on your predictive model increases. So how can we in practice it is difficult to answer the causal question. Why? Because it is effectively very difficult. Oftentimes what we see is just an observed response. Proving causality is very difficult proposition. One possibility is randomized experiment, randomized case control experiment. Oftentimes in economics nowadays it's very popular, RCT, randomized case treatment studies or causal treatment studies. It is well known in the statistics literature for about 100 years now, and in this randomized case control experiment might help us establishing the causal relationship between a feature and a response. But there could be a situation where simple ethical construct, for ethical reason, you cannot run a randomized case control experiment. For example, if you want to, how a randomized case control experiment happens. So for example, you want to check the efficacy of a vaccine. So what you will do, randomly some patient will come in the study. You will toss a coin. If it is head, a patient will get a vaccine. If the tail, then the patient will get a placebo. And you do it for say few hundred patients, and at the end of the day, you will observe the patients for a year or 2 years or 3 years, and then you will see that how many of the case group have developed the disease, and how many of the control group has developed the disease. So, and that will give you a sense of whether the vaccine is effective or not. And but the same study you cannot run on certain experimental situation. For example, you want to test if smoking causes cancer. Now we have enough evidence that very likely smoking do causes cancer. Now you cannot just toss a coin. You say that okay, you group of people will do smoke and you cannot smoke. If you know a treatment may cause harm to a group of people, then you cannot run that study. So randomized case control experiment has its limitation. Now, Granger causality can be used to make some causal treatment with some limited effect. So, Granger causality helps us to understand if one time series is useful for predicting another. So, question that Granger causality try to answer: does one time series cause another, controlling for lags? This is the question that we try to answer, we try to figure out. So we start with the basic univariate Granger causal test. We have two time series, say yt and xt, and t is from say 1 2 up to n. So t is the time point. Are the lags of predictive y controlling for lags of y? Are the lags of x can predict the y for the lags, controlling the lags of y? So how you do that? You create yt. You want to predict yt equal to beta naught, beta 1 yt minus 1, beta 2 yt minus 2, plus dot 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 beta k yt minus k, plus gamma xt minus 1 plus gamma 2 xt minus 2 plus gamma k xt minus k. You see, this model is completely linear in parameter. We can easily find the estimates using OLS estimator or any standard methodology like lasso or elastic net. Now, what this model means? This model means basically that after taking, so whatever the variability in yt, many of the variability getting explained by its own historical behavior of yt minus 1, t minus 2 up to yt minus k. After that, if still there are some residuals that can be explained by xt minus 1 or xt minus 2 or xt minus k, then we can say that a lag variable of xt minus k or some lag variable of x time series do have some effect on y, or we can say some lag variable of say t minus k do have some effect on yt. So this is, or we can say that Granger causes yt. Now, how we do that? So what we do a test for Granger causality. If the gamma 1, gamma 2, gamma k, what are the gamma? Gamma, remember that gamma is these coefficients. These coefficients are all 0, that means none of the x have any effect on the y. So y is only function of its own historical behavior. And if any one of the gamma e, at least one lag of x is additional, provide some additional information to y. So any at least one gamma e non-zero, that means at least one lag, any one lag of x do have effect on yt. So if that happens, then we can say that time series x Granger causes time series y. Now, how do we choose the number of lags? It is a trade-off between bias and versus the statistical power. With too few lags, we can find residuals autocorrelation. It may give us a bias test. With too many lags, it might incorrectly reject the null due to just some spurious correlation. So again, what you have to do, you have to choose different values of k. You have to do the test, and also you have to calculate the mean square error, and you have to check in the out of the sample whether what is the RMSE or what is the adjusted R square of the data, and then you have to choose a correct kind of lag where you should stop, and for that lagged model, if the x time series has any effect on the y time series. But the question is, okay, this is just a statistical test we are talking about. But from this statistical test, can we conclude that x causes the future number of y, or x causes the y? There are several potential issues when making causal statement. First issue could be confounder. There may be some other variable z which is correlated with x, and that is the true cause of y, and what you are seeing is just some spurious correlation. It is not really the main correlation. There could be a lead drag relationship or feedback loop, like xt minus mu cause yt and yt causes xt plus 1. Similarly, yt minus 1 cause xt and xt cause yt plus 1. And this feedback loop could be a problem to then who causing whom. Is it the causality is both way? You have to conclude in that way. So, and the final is spurious correlation between the two variable, but it was just a coincidental. So you have to be very careful when you are making such causes. So there is an air quality data set which has daily air quality measurement in New York from May to September 1973. Here is the data set, and the ozone. In that there are two variables. One is ozone variable, another is the temperature. Okay, how the temperature behaves, and during that time how the ozone actually behave. So question is, if temperature causes the movement of the ozone, it does have the ozone level, and ozone level has some, ozone is a greenhouse gas. So question is whether can we is temperature going to do causing the level of ozone. So there is in library LM test, there is a function called Granger test. We can use that. Just simply ozone follow temperature order 1 data equal to air quality, and then it simply runs the model 1 ozone, and then you can see the p-value for the test is extremely small. So we reject the null hypothesis that none of them have any effect. So that means the temperature does not have an effect. So we reject that. So what is null? Null is temperature does not have an effect. Does not have an effect on ozone versus alternative temperature does have effect on ozone. So since p-value is too small, so we reject null hypothesis, that is, we reject this guy, and we say that temperature does have an effect on the ozone. Then this model was done with only one lag. What about going for lag 2? And we did it with the lag 2 here, and now still it rejects the null hypothesis. And then we calculated the AIC of model 1 and AIC of model 2. Between the model 1 and model 2, this is better model because AIC is minimum this case. So we should choose our inference from the model 2. So now we will stop here and we will go to the do some hands-on. So see you in the next video with hands-on. Thanks.